Welcome, and in this video we're going to get kind of some nitty-gritty how do I do my homework problems. So example 1, this is the first type of homework problem that you might have on your web assign. You have to use the given values to evaluate all 6 trigonometric functions. So here's what I know. They want me to find the sine of theta. They want me to find the cosine of theta. They want me to find the tangent of theta. Please note you don't have to do your work like me. I'm just trying to organize and present. We need to find the reciprocal. I like to write the reciprocals directly across. We have to find our secant and our cotangent. All right, so what I know is they gave me that the tangent was root 3 over 3, and they gave me the cosecant was 2. So without really doing a whole lot of work, I automatically know what the sine and what cotangent is because they're just their reciprocals. So the reciprocal of 2 is a half. And then if I flip 3 over root 3 and I rationalize, I get 3 root 3 over 3, which is just root 3. So really what we're working for is to find the cosine and the secant. I do want to let you know that you are absolutely entitled, look at your text, you can use specifically the Pythagorean identities if you would like to find those. In other words, there is definitely more than one way to find the cosine and the secant. I'm just going to show you what I have found that students find the most direct. A lot of them like to draw a triangle. This is the study of trigonometry. So if you think about your 4 quadrants, really what's imperative right now is getting your triangle in the right quadrant. So if I know the cosecant is 2, that means it's positive. So all trig functions are positive in the first quadrant, and cosecant and sine are in the second quadrant. So that means I'm not going to draw that triangle in the third or the fourth. Then I'm told that the tangent is also positive, and tangent is positive in the first and the third, so that means my triangle has to be written in the first quadrant. So when I draw my triangle in the first quadrant, I know that the cosecant is going to be hypotenuse over opposite. Hypotenuse over opposite. And if I do Pythagorean theorem, I get 1 squared plus x squared equals 2 squared. So x squared is equal to 4 minus 1. So that is root 3. You also could have ascertained that information by the tangent. Then when I do my cosine is going to be adjacent over hypotenuse. So that's root 3 over 2. And its reciprocal, when I rationalize, is going to be 2 root 3 over 3. And there are my 6 trig functions. Let's move on to a new type of problem that really is going to help set you up to verify full-blown identities in the second half of this lesson. We're going to use the fundamental identities to simplify the expression. And what I am not going to do on this video is I'm not going to graph each one. I'm going to let you do that. Basically, if you graph the problem that I present and you graph the solution, they should be the same. And I'm going to be frank, it's just going to be out of time so that you aren't on a video forever. I'm going to let you do that portion. So when you simplify, sometimes we have to substitute a different expression. Sometimes you factor, sometimes you get a common denominator. But staring and doing nothing is not going to help you at all. You will start to get the hang of this. I decided to give some examples that were a little bit more on the more challenging side. But here we go. Example 2. They want you to simplify the cosine beta, tangent beta. If you do not like betas, switch them to thetas or x's. So if you don't like those betas, friends, it's okay. Just switch it to cosine tangent of x. So you're like, what am I supposed to do to simplify? Well, a hint is if you are stuck, if you can't even begin, try to put everything in terms of sine and cosine. So I already have a cosine of x. I'm not going to mess with it. So I'm going to rewrite it. But I can re-represent the tangent of x using a quotient identity and rewrite that as the sine of x over cosine of x. So when kids go, how did you know how to do that? I tried something. That is what is, I guess, the beauty of identities, and what also is difficult. I can give you tools, but it is not a recipe. So what can I do next? I can do an algebraic step. Well, I know that the cosine of x over 1 times 1 over cosine x cancels, and this simplifies to the sine of x. Again, I'm going to leave it to you to graph, but if on Desmos you put in f of x, or if you put in cosine x tangent of x in that first slot, and then you put in the sine of x, you should verify that you could get the same graph. Okay, example 3. So when I get to this example, sometimes kids are like, okay, what in the heck do you want me to do here? You got a couple of choices. Getting everything in terms of sines and cosines really isn't an option, because everything is already in terms of sines and cosines. So I am going to offer one strategy where look to factor out a GCF. And the reason I'm splitting my paper is I am going to show you how to do this an alternate way. All right, if you notice, this is one term, this is your second term. Both terms share a sine of x. What am I going to do next? I am going to write what's left, and after I factor out a sine of x, I get cosine squared x minus 1. Again, you can check your answer. If you would distribute, you should get that original expression back. All right, well, what do I do from here? Are you done? No, we can do more. All right, the cosine squared of x minus 1, well, I can replace the cosine squared of x with the Pythagorean identity 1 minus sine squared of x. Furthermore, I can simplify. These cancel, and I am left with the sine of x times a negative sine squared x, and I can multiply those to be a negative sine cubed x. Was that the only way to get there? Absolutely not. And that is what is, I guess, the beauty and yet frustrating part of identities. Some kids have said, well, you factored, but do I have to do the factoring? Can't I just look at the cosine squared of x? My brain processes this where maybe I can put everything in terms of the same trig function. That's something else you can look for. Maybe I can put this all in terms of sine. So I can do the sine of x and then replace the cosine squared of x with 1 minus sine squared of x. Next step, I can distribute. So this is going to give me the sine of x minus the sine cubed x. And then I tack on my minus sine x. The sine x's cancel, and I still end up with a negative sine cubed x. All right, let's keep on trucking. All right, welcome to example 4. And we're looking at this and thinking to ourselves, in example 2, our strategy was, hey, why don't you put everything in terms of sines and cosines? In example 3, we learned about factoring out a GCF and putting everything in terms of the same trig function. Unfortunately, none of those strategies are going to work in this problem, which is why I selected it as an example. What you do have, though, is an opportunity to factor. So think about this. Let's get the highlighter off. If I have x squared minus y squared, that's going to factor as a difference of two squares into x plus y, x minus y. It follows from that factoring pattern that if I have x to the fourth minus y to the fourth, it's going to factor as x squared minus y squared, x squared plus y squared. So along those same lines, if I have the secant to the fourth minus tangent to the fourth, I can factor it into the secant squared of x minus the tangent squared of x times the secant squared of x plus the tangent squared of x. Now, something might look a little familiar. Now I have everything squared. So since I have it squared, we have a Pythagorean identity that relates secants and tangents. It tells us that 1 plus tangent squared of x equals secant squared of x. Well, if I subtract tangent from both sides, then 1 is equal to the secant squared of x minus the tangent squared of x, so all of this is 1. So I will tell you, this is where you can kind of get into the vortex and you can keep going and you keep going. If I was on WebAssign, the final answer to this is just secant squared x plus tangent squared x, or this factor. But I mean, if you wanted to, you could keep going. And this is what I mean, where some kids kind of just get into the vortex, I call it, where you just kind of spiral. I could also, for the secant squared of x, I could substitute in 1 plus tangent squared of x. And so if we were not in a virtual setting and we were taking a traditional pen and paper quiz, if a student told me that this simplified into 1 plus 2 tangent squared x, friends, that's equivalent. I would take it. Even though you didn't have to go any farther where that's okay, that's equivalent. Likewise, if I wanted, I could keep the secant squared of x, and instead of the tangent, put in 1, that was incorrect. Let me erase that. I could put in secant squared of x minus 1, and that would give me 2 secant squared x minus 1. And like I said, you can keep going and going, but all of those answers, they're all equivalent. They would all be full credit. All right, welcome to example 5. So again, hopefully you're noticing a trend. We're not just doing examples to do examples. What's my takeaway from this problem? Your takeaway is that we have 3 terms. So this is going to be basically trinomial form. So what do I mean by that? Let's talk about maybe a problem we're a little bit more familiar with. If I gave you 1 minus 2x plus x squared, and I asked you to reverse FOIL or factor this, well, the way I get the first term is 1 times 1. The way that I get an x squared is an x times x. Both are negative, so that if I would first, outer, inner, last it, I simplify back to what I started with. All right, so let's take this one more step further. What if I have 1 minus 2x squared plus x to the 4th? Same idea. How do I get the first term of 1? 1 times 1. How do I get the last term? X squared times x squared. Both have to be negative so that when I do my first, outer, inner, and last, it simplifies back to what I started with. So that is what I'm going to do here. I get a 1 by 1 times 1. I get a sine to the 4th by sine squared times sine squared. Next, they're both negative because if I would first, outer, inner, last it, I get back to what I started with. Next, I know that sine squared of x plus cosine squared of x equals 1. So that means cosine squared of x equals 1 minus sine squared x. So this is cosine squared of x. And this factor is also a cosine squared of x, leaving me with a final simplified answer of cosine to the 4th of x. And last but not least, we have our last example, example 6. And why did I show you this? Again, I don't know that throwing this into terms of sines and cosines is helpful because I don't know that you really want to mess with 1 over cosine cubed of x as well as some additional rational expressions. I don't have a GCF. This is already in terms of secant, so it's in one trig form. This is not a difference of 2 squares. This is not trinomial form. But what it is it's 4 terms. And when we have 4 terms, we use the factoring by grouping strategy. So how does that work? Well, let's remind ourselves how this works with regular algebra. If I gave you x cubed minus x squared minus x plus 1, I would look at the first 2 terms and factor out a GCF. Then I would look at the back 2 terms and I need it to match that parenthesis, so I'm going to factor out a negative 1. And then now you have 2 terms where both of them share an x minus 1, and when you pull out what's left, you're left with an x squared minus 1. So what does that look like in our problem? Well, if I look at the first two terms, they share a secant squared of x in common, leaving me with a secant x minus 1. Then, if I look at the back two terms, I'm going to take out a negative so that I get a secant x minus 1. Again, this is one term. This is a second term. What is it that both of them share? They share this obnoxious binomial secant x minus 1. And if I take those out, if I take out what they share, what are you left with? You're left with a secant squared x minus 1. This is one of those where you could again go into the vortex, but the fact that that has a squared term leads me to believe that maybe I should look at my Pythagorean identities. And if we know 1 plus tangent squared x is equal to secant squared of x, then I know that the tangent squared of x is equal to the secant squared of x minus 1. So final answer is secant x minus 1 times tangent squared of x. I know your note says this. We are not doing that activity. I forgot to take that slide out. So you are now ready to do your Unit 1 Lesson 4 web assign. Enjoy.